Hello, ladies and gentlemen. Welcome on first summer series webinar, Workflow for Preloaded Bolts. My name is Vít Hurčík and I'm going to lead you through this webinar today. I'm here on behalf of IDEA StatiCa company and I'm product engineer. For you who are here for the first time, you can place the questions into the control panel of the GoTo application. I will try to answer the questions at the end of the webinar, or I'm going to answer them after the webinar by email. And let's start with the basic topic. Preloaded bolts. How they are meant to be by the Eurocode. I'm sorry for the problems. I will start again. Preloaded bolts according to Eurocode. Benefits of preloaded bolts: increased rigidity of joints in non-slip service, loosening of bolts due to vibrations, and better fatigue performance. Higher tolerance for fabrication or erection usage of clearance holes or slotted holes. I hope now it's better and you can see the screen. How does the preload connection work? Bolts are tightened such that high tension in a bolt is developed. Then the plates of the connection are clamped together, and the shear force transfer is achieved through friction. One of the most important part is the table 3.2 in Eurocode, because Eurocode is telling us what we have to use as a limitation for the code check. If we talk about the tension connection of preloaded bolt connections, then it's easy. But if we talk about shear connections, then the situation is more difficult. Engineer has to decide if he going to use B category of the bolted connections, because then the code check is different and the slip resistance must be checked at the serviceability limit state. If the engineer chooses the C category of the bolted connection, then the slip resistance has to be checked at ultimate limit state. And I'm going to show you this in examples further in the webinar. Well, we are going to talk about how to basically set up IDEA StatiCa connection to deal with preloaded bolts. The first part, you have to set up your manufacturing operation. That's the basic setup. And you can start with the right bolt grade. 8.8 or and 10.9 must be used. Then there is a must to choose right parameter. Shear force transfer must be set to friction. Then the IDEA StatiCa connection will perform the code check of the preloaded bolts. If you are more advanced user and experienced engineer, you can play with more factors, more parameters. Eurocode is more variable for partial safety factor for C and B category of the bolted connections. So you can use different value of partial safety factor gamma M3 and make some savings. This is available in the code setup of the application. Moreover, as a engineer, as a designer, you can prescribe friction between the surfaces. And according to Eurocode, you can choose slip factor according to table 3.7, friction coefficient. IDEA StatiCa by the default uses 0.3. Moreover, pretension force factor. Design slip resistance is a factored value of inserted or created tension force in the bolt. And tension force in a bolt, it's simply calculated by parameters of the bolt, area and yield strength. And this pretension force factor is designed or stated by the manufacturer or the code, and you can play with that if you need to also. Okay, let's do the practical demonstration. I prepared for you two examples. First one will be a splice connection, and I'm going to design it as a B category of bolted connection. That gives me a different scenario because I have to use two models. First model, I'm going to check according to slip resistance in serviceability limit state. Second model, I'm going to check for bearing resistance in ultimate limit state. And that's the important thing. Second will be bracing connection, and that will be C category of bolted connections. For this, I will need only one model, and I'm going to perform a code check of slip resistance in ultimate limit state. So let's change our focus to application IDEA StatiCa connection. Okay. I have prepared for you this beam splice project. I have here two load effects, one ultimate limit state and second serviceability limit state. And then I have three splices. If I'm going to use friction bolts, I need to change here the parameter shear force transfer to friction. And I'm going to turn off the ultimate limit state, because in the first part, in the first model, I'm going to check preloaded bolts, the slip resistance for serviceability limit state values of the internal forces. So I'm going to calculate and you can see that the code check is okay. It's valid. We passed the limits, but we are really on the edge. Here is the design slip resistance, 21 kilonewton-meters, and the resultant of the bolt shear force is about 90 kilonewtons. But I'm really on the edge, and I'm an experienced user, so I can change the value of partial safety factor to 1.1, and that helps me because that saves 15%. And I need to be more on the safe side. And that's great. Now my design slip resistance increased and I'm much more happier than before. Then I need to check the second model. So I'm going to create a copy of my project item. Here, I'm going to reset the settings, the project settings, turn off the serviceability limit state and turn on the ultimate limit state. And I'm going to change back to tension shear interaction because I want to code check different thing. Okay, then I'm going to calculate this project. And let's check out what's here. I have here the plate bearing resistance, and that's the point. In the second step, I need to check second model for bearing resistance in ultimate limit state, and that's it. That's the way how can I perform code check of one connection 2 times. One time for slip resistance in serviceability limit state and second time for bearing resistance in ultimate limit state. That's the end of my first example, and let's proceed with a second one. I'm going to choose this bracing according to Eurocode, and we are going to check it according to slip resistance in ultimate limit state. Let's say these internal forces are my ultimate limit state. And then I can change this for pretension or both connecting plates. That's a friction. I just started the calculation, the analysis, and in a few seconds or dozen seconds, we are going to have the results. Every time my colleagues and I, we are giving you a hint to check out the process of the iteration. If the iteration process goes fast, increases the percentage equally to 100% and stays there, probably the model behaves all right. If the percentage goes down, like in this example, something went wrong. We are on the edge of the capacity of the connection, for example, and something is yielding. Even now, I can tell you that the connection will not pass the code check. And we have here results. Preloaded bolts doesn't pass the code check. Why? Check out the design slip resistance, 21 kilonewton meters, but the acting resultant on the shear force is 30 kilonewton meters, and that's not good. I'm not satisfied. So I'm going back to design, and I'm going to choose different bolt grade, different with the same size of the bolts. That will give me higher yield strength and higher pretension force. Remember the one which I showed you a few minutes before. I'm going to calculate it. Now it will be better, but I'm curious about the result. Meanwhile, the questions are here. I have more of them, so I will react at the end of the webinar. Okay, the result is much more better, 116%. My slip design resistance increased, and that's far more better. I'm at 26 kilonewtons. And one more, I can increase the friction coefficient in slip resistance according to the Eurocode, and let's say I'm going to save 10% more. So by this, I'm going to achieve again increased slip resistance because there will be higher shear force, higher resistance. And the iteration process goes fast, really 100%, and the results are here really quickly. And our design slip resistance is almost 35 kilonewtons, which is giving me a higher value than the acting shear force, and the code check is okay, and I'm happy, I'm satisfied. But that's not the end of the example, because I can design, for example, slotted holes in the IDEA connection. Let's say I need it for erection purposes. So let's design slotted holes here in the connecting plate. For these bolts, I will choose slotting in this direction, and I'm going to increase the size of the slotted hole. And the same thing I'm going to do for the second splice connection. Okay. We are going to check if all slotted holes are inserted. You can see them here. They are here. And according to that, it should change the code check, of course. Let's try it. Now the code check didn't pass. And why? Because design slip resistance is decreased almost 14 kilonewtons. And why? We can check it out in a detail. Shear resistance check. Here is the point, KS factor. If you are going to design slotted holes, this factor will not be 1 as it should be for regular sized holes, but the value will be 0.63. An IDEA StatiCa connection application detects it automatically and inserted the right value of the factor. And that will help you to speed up your design process. This is the end of my second example, and I'm sure there is a lot of questions. So let's jump back to presentation, and we are going to answer some of them. So give me a few seconds. Attendee is asking, if I don't need slip resistance, can I choose the coefficient 0? Well, in that case, it won't work. If you don't need a slip resistance, don't turn off the friction. Then it will be, the model will behave in a same way like typical bolted connection. You can use bolt grade 8.8 or 10.9, but without the slip resistance code check. The pretension force can be changed by the coefficient in the advanced setup, and you can access it easily here in the code setup. Here is the pretension force factor, but this setup is recommended only for experienced users or engineers. Where are the values friction coefficient in the slip resistance came from? Well, they came from code, Eurocode. Here are the friction coefficients, table 3.7, and they are the explanation will be in the reference in another code according to this table. And here the 0.7 comes from the probably the parameters of the bolts. It can be found in the codes also. And there are more questions. How to decide if the connection should be B or C type? Well, that's your engineering point of view. You are a responsible engineer and you have certain needs. The structure must behave in some certain way, so you have to choose which behavior is for you much better. It's up to you, up to the engineer. We are going to the end of our time slot for this webinar, so I'm going to back to presentation, and other questions I'm going to respond or answer by email. So don't be afraid, you will get your answer. After the webinar, there will be a short survey. Please fill it. The recording will be available at the YouTube or at our homepage. If you are a trialist or you are not asked yet, you can find our trial version at ideastatica.com. Please visit our support center. Next webinars will be during the whole summer. We prepared it for you summer series. Next webinar will be July 29th, and it will be footing connections, quick and easy. Next summer series webinar for concrete will be about the BIM link with axis and IDEA StatiCa detail. So stay tuned, please. If you are interested, we have IDEA StatiCa Campus, so you can be a certified IDEA StatiCa connection user. You can try it. And that's the end of our webinar. Thank you for your attention today, and sorry for the small technical issues at the beginning. Have a nice day.